Hello everyone, and welcome to our webinar, Introduction to Rheology in Mining. So I'm Charles Villiers, Principal Engineer at ATC Williams, and I'll be assisting Paul today. Firstly, I would like to go over a few items so you know how to participate in today's event. You are now listening using your computer speaker system by default. However, if you would prefer to join by phone, just select telephone in the audio pane and the dialing information will be displayed. Now, also you can submit text questions to Paul at any time by typing them in the question pane of the control panel. We will collect and address them during the Q&A session at the end. Now, I would now like to introduce briefly Paul. He is working with ATC Williams and has been involved in pipeline and flow process consulting and research for over 30 years. He has also pioneered a new Reynolds number design approach for yield stress materials and the sheet flow paradigm for free surface flows of mine tailings material. I know just about ATC Williams, over 500 tailing storage facility designs completed in Australia and overseas over the last 34 years. We have offices in Perth, Melbourne, Brisbane, Latin America, the Middle East, and operate in all the main mining regions in the world. Our Melbourne-based tailings laboratory facility is also a strong base for our traditional focus on research and development. And now, Paul, over to you.
Thank you, Charles. Welcome everyone to our webinar on the rheology and introduction to rheology and how it can be used usefully in mining. I'll be giving you an introduction, and we'll talk about rheology, focusing on applications in mining, and then we'll look at some practical design considerations. First of all, what is rheology? Well, rheology is the study of the flow of material. This comes from two Greek words, rheo, flow, and logia, which means study of. So rheology really is the study of the flow of material. Materials flow when a shear stress is applied. And if you look at the graph on the right-hand side here, we've got the relationship between shear rate and shear stress. And if we have a very simple, what we consider to be a simple material, a straight line relationship passing through the origin, where the shear rate is directly proportional to the shear stress, and the slope of this line is defined as the viscosity. So that is the fundamental definition of viscosity, which is shear stress divided by shear rate. This is for the simplest of fluids, which we know, which we call Newtonian fluids. And as you'll see from this diagram, the viscosity is constant. The slope of this line is constant. I'm going to emphasize again, it does pass through the origin. And this is not changing. So the shear rate and shear stress don't have any effect on the slope of this line. And that's an important point to bear in mind. So that's constant over whatever we wish to do with this material. Now, where will this be useful in mining? First of all, in any of the flow processes which we have in processing plants, in mixing, mass transfer, all of those sorts of things which go on in processing plants, those will all be affected by the rheology of the material because that affects how it flows. One of the most interesting applications is when tailings is transported from the processing plant to the storage facility, and that is usually done using a pipeline or launder, and this process is dominated by the rheology of the material because that is how it flows And we need to have a good understanding of the rheology in order to design, operate, and control the flow and disposal in the storage facility. If we just look at these diagrams, if we have a conventional storage facility, fairly low concentration, and a very flat surface, and a rather large bund, that is typically what we will see. If we are able to increase the concentration of the tailings material, we will be able to increase the slope of the beaching material. And that means we will be able to increase the storage capacity of the storage facility. And that's a really important part of mining to be able to do that. And if we just go to the logical extreme, if we have filtered tailings, we can stack it up at its geotechnical limit like that to get the steepest. So if we can understand and if we can manipulate the rheology to suit what we want, that would be a really important part of the tailings storage process. Looking at some of the practical issues now. Rheology, we're going to be talking about mainly in connection with pipe flow. And one of the recent, or the most important or largely used design approaches for tailings pipelines and any pipelines using rheologically interesting materials, that developed by Metzner and Reed. That was done way back in the 1950s, and it was a really good approach and has worked very well for many materials over many years. But we'll see how well it works when we need to use it for tailings materials, for example. Now, what they did, Metzner and Reed, was develop a process for interpreting a pipe flow test. And they would use this approach of theirs to determine two, we could call them rheological constants, K prime and N prime, and then they would use them to determine the critical velocity. In other words, where does the flow change from laminar to turbulent in a given pipeline? What would the laminar flow head loss be? What would the turbulent flow head loss be? And then we could use that to plot a system curve, which is a very important part of the design process. And then we could determine the pump operating point and get the power requirements for that material. What is important here is that what impact does a yield stress have? Yield stress fluids, also called viscoplastic fluids, are in almost every tailings facility that I've come across. And so what impact will the yield stress have? Can we use the Metzner-Reed approach? And I've plotted on the right-hand side here a typical bulk rheogram in terms of the bulk shear rate and the wall shear stress. And the interesting bit is that what Metzner-Reed did was assume it would be a straight line relationship. And that's where the two constants, the K prime and the N prime, come from. But if you have yield stress, this line is curved. It's important to note here that we were working on logarithmic axes because that's what Metzner and Reed used. And that's when it starts to get interesting, because now we have a curve, and that is a direct result of having a yield stress. And that's where things start to get interesting, and what we're going to look at specifically today, because we're going to use that to get the pump operating point and the power requirements. So the center of this problem is the yield stress. How are we going to use it? What is the significance? will it work? And if it doesn't work, what are we going to do about it? I think that's the essence of it. I'm reminded of a very famous American politician, Al Gore, who formulated a most inconvenient truth. He was talking about climate change, which is not relevant really to what we're doing today, but I wanted to tell you about something which I've called a most convenient lie. When you first started studying science, early school days, I'm sure that one of your teachers said to you, all matter consists of solid, liquid, and gas. And that's an interesting starting point, but the truth is that there are quite a lot of materials that don't really fit into that description, such as lipstick, Vegemite, toothpaste, jam, and they have both solid and liquid properties. If we look at the two extremes, a perfectly well-behaved solid is a Hookean solid. If we look at this graph of stress against strain, then in this region here, where we have a straight line relationship between stress and strain, we have materials which obey Hooke's law, and that's a well-behaved solid. And if we have a Newtonian fluid, then that's a well-behaved fluid. Many materials lie in between. And so we find that if we take a material, even materials like steel, and we stress them far enough, they will actually become plastic and start to flow. And this combination of solid and liquid materials is something we're going to have to deal with. We'll do a demonstration looking at clay suspensions, and we'll use three concentrations, a low, a medium, and a high concentration, and that will show us where the solid properties start to come in and how we're going to deal with them. Before we get into this, I just want to point out a few things to the relationship between concentration and pumping power. So if we've got a given solid's throughput and we have a low concentration, the power requirements are going to be quite high because we're pumping a lot of water along with the solids. If we have a very high concentration, the pumping power is also going to be quite high because we have such difficult viscous material to pump. And as engineers, we're always looking for where is the optimum and how close can we get to that operating point, to the optimum. And that's what we're going to look at, these three: low concentration, a medium concentration, and then a high concentration. Just to stress the point that we have some solid characteristics, what we've done here is take the high concentration one and turn it upside down. And in this particular case, the solid properties were in fact so obvious that it didn't even flow out after a few minutes. We didn't leave it there that long, but there it is. So you can see distinct solid characteristics over here. The other thing is looking at the surface of these materials, the low concentration and the medium, they have flat surfaces, whereas the high concentration material, you can see the surface is still disturbed from the mixing instrument that was used to mix it, and it is definitely not flat, indicating the existence of a yield stress which is dominating its behavior in this case. Let's just go back to what I said near the beginning. What is a simple fluid? The ratio between shear stress, the relationship between shear stress and shear rate, and the straight line passing through the origin, which is defined by physical definition as the viscosity of the material. So that's a simple material, and that is typical of water, oil, materials like that. Once we start to get into mining slurries and suspensions, we have to start dealing with, as I said earlier, the yield stress. got that same diagram, shear stress against shear rate. We'll give this diagram a name now. We use the name rheogram. It encapsulates pictorially the rheology of the material. And we're going to start talking about yield stress in this sense. You can see that these do not pass through the origin, and I think that's important. So materials that are not Newtonian, we refer to them as non-Newtonian, so they're not a straight line passing through the origin. And we can see even if they curved but pass through the origin, we have some non-Newtonian characteristics. That's known as pseudoplastic. But if we have this offset here, then we have distinct solid characteristics encapsulated by the yield stress. And what's important to note is that if you apply shear stress which is lower than the yield stress, then what we get is solid behavior. It does not flow. To get the material flowing, we have to apply shear stress which is greater than the yield stress. And two of the materials which we're going to be talking about, Bingham plastic and yield pseudoplastic, they do not pass through the origin. They have yield stress, so there's an offset up the vertical axis here. And Bingham plastic is a straight line relationship, whereas the yield pseudoplastic is a curved line with a yield stress. And just to remind you, one of the things there is that it will not form a flat surface because we have some three-dimensional microstructure which gives it some rigidity, provided that we have stress applied lower than the yield stress. We have solid behavior, and are we going to be able to deal with that as we use our pipe flow design procedures? Well, first of all, let's go a little bit further and fit an algebraic form to that. So this is the graphical form, and that would be the algebraic form of what we call the yield pseudoplastic or Herschel-Bulkley rheological model. And that will describe this curved line here, the yield pseudoplastic. What I've shown here, for matter of convenience, is the same diagram, but with logarithmic axes here. And we see how the different shapes are formed. And so we can take this equation and simplify it down to two constants, because that has three constants in it. And the Bingham plastic is by setting n equal to 1, that gives us a yield stress. And then a straight line relationship, or a pseudoplastic, which does not have a yield stress. So it would pass through the origin there, and which gives us a straight line relationship on the logarithmic plot here. So that's the essence of the rheological model, which is one of my favorites and which we'll be using later on. If we then use what we know about viscosity and say, well, we'd like to know what the viscosity of this material is by performing the ratio between the shear stress and the shear rate, then we can determine the viscosity, and that would be that algebraic equation just transformed as a viscosity equation, and plot that against shear rate and viscosity, and what we get is all of these monotonically decreasing functions, and that is an interesting phenomenon which we refer to as shear thinning behavior. So as the shear rate increases, these materials have less and less viscous resistance to flow, and that's why we get this shear thinning behavior as the viscosity decreases with increasing shear rate. The significance, let's see. If we apply the well-known and much used Metzner-Reed approach to a viscoplastic fluid, will it work? Will there be any problems, and how do we deal with it? So we're going to do a classwork example now by using the Metzner-Reed approach with a yield stress fluid. did, we take some pipe flow tests. So we've done a test. A test has been performed specifically for pipeline design purposes. It's a clay material at a relative density of 1.3, and we've performed it in a relatively small pipeline in the laboratory, 13 millimeter diameter. And then we will use the Metzner-Reed approach, which starts off by plotting the bulk shear rate and the wall shear stress. That's the bulk shear rate, wall shear stress. And there's our material. And what's interesting here is that we've got a laminar flow, and then it goes into turbulent flow. And that would be the critical velocity there. That's on linear axes. We plotted on logarithmic axes. That's the same diagram as above. And then in the laminar region, we'll fit a straight line so that we can start using the Metzner-Reed approach. And that gives us the values for the two constants as shown here. And then we can use these constants and do the calculations using Metzner-Reed approach. And in particular, what we're interested in is the critical velocity calculation. That's where it changes from laminar to turbulent flow. And the calculation gives us a critical velocity of 2.9 meters a second at the Metzner-Reed Reynolds number of 2,100. And we can take this back and then compare that with the measured critical velocity. So that's the diagrams you saw earlier. There we have the Metzner-Reed fit, and there we have the prediction of the critical velocity. And unfortunately, that's where it should be. So we have some significant error here, and that's going to be something which we need to deal with and start discussing. That's the same diagram on logarithmic axes. So what we have here is an error exceeding 20%. The problem is that this error increases with diameter. We've used a small diameter pipe, 13 millimeter. We would, in industrial applications, often be dealing with hundreds, several hundred millimeter diameter pipe. So that error will increase with diameter. We have a problem, design implications, and we will need to change the design approach. So what we're saying here is that the Metzner-Reed approach, which works well, does not work well, in fact, with yield stress fluids, and we've got a problem with that. So we will need to start using the yield stress-based rheological models. I will be using the Herschel-Balke model and the Bingham plastic model, and we will start using that for the development of laminar flow, turbulent flow, predicting critical velocity, and that will be the subject of the coming webinars in the future. So what we'll do is start off. We've shown today that we will need to use a viscoplastic rheology because the materials we are dealing with have definite yield stress. They have some solid properties, and we will need to include that in the way we do our design. And then we can use that viscoplastic rheology to model laminar flow, transitional flow, turbulent flow. And then we can start, once we've started the fundamentals of pipeline design, going into some practical applications, done some interesting work with valves and fittings, and this material flows through valves and fittings. How does that affect it? When it flows through a pump, how does the performance of the pump change? And the interaction between pumps and system curves are also something which we will need to look at, and that will be something that we will be using the rheological modeling for. So the rheological modeling might seem a little bit abstract to start with, but it has a very, very important practical application for the design, control, and operation of the tailings and the processing plant flow processes. I think I've done a lot of talking about these things. Let's see, how do we measure rheology? Well, rheology is measured in a rheometer, and we can show here some rheometer readings. The red diamonds here show what we would measure, and that is from a rheometer. What do we do with that? Well, the first thing I would do with this is fit a Bingham plastic straight line to that data. This is shear rate against shear stress, and that line would be the Bingham plastic rheology for this material, and then we could use that rheogram information for pipeline design, just to show you where does this information come from. So, leading discussion now. We've tried the Metzner-Reid approach using the yield stress fluid, which is typical of many mining slurries, and it does not work because this Metzner-Reid approach cannot adequately accommodate yield stress. And in particular, what we had was under prediction of the critical transition velocity, which is an important fundamental part of the design process. So we will need to deal with that. As we need to go to a viscoplastic rheology, we're going to have to accommodate the yield stress, and we're going to have to develop modeling which will do that. And we will use the Herschel-Balke rheological model, and where possible, we will simplify that to the Bingham plastic rheological model, and then we will use these to model the flow and the processes that we will need for processes, pipe flow and launder flow, pipe pump flow and flow and fittings, and so on. So, in conclusion, what is rheology? Rheology is the study of how materials flow. Mining slurries can have some solid characteristics, and that's really important to bring into the rheology. And this presence of the yield stress must be taken into account, and it's really important. If we look at these two applicators, this is a conventional storage facility here. We see a very flat surface and two rather large embankments. And if we, for example, go to a central thickened discharge where we exploit the rheological characteristics of the material, then in a thickened discharge system, we can have considerable increase in storage capacity and a very different approach to the storage facility management and operation, and that's really attractive from a mining perspective, which we'll be looking at. Thank you. Thank you for your attention, and I'd be interested to hear if you have any questions. Thank you.
Okay. Thank you very much, Paul, for the presentation. So we're going to answer the questions submitted today. By the way, you can still submit questions on the questions pane in your attendee control panel. Okay, so Paul, I've got a first question. Someone was asking if how common it is to pump high density tail strings, and they were mentioning something like 70% solid content. Can you say a few words about that?
Yes, that's an interesting question. It certainly is possible. Depending very much on the density of the solids, what would be the volumetric concentration, because that's what we really are interested in when it comes to rheological characterization and flow analysis. So pumping at that kind of concentration is certainly possible. In the modern context, where we're trying to save water, save energy, and manage storage facilities in the best possible way, being able to manipulate the rheology, the flow characteristics, is very important and very attractive. And certainly, I believe we have seen recently more and more of these higher concentration applications in industry, and I think they are starting to show the benefit of being able to operate at higher concentration when needed, and I think we're going to see a lot more of that. Thank you, Charles.
Thank you, Paul. Question, so it's regarding the Metzner-Reid approach. In which case does it work really well, or can you apply efficiently?
Metzner-Reid will work very well if you don't have yield stress, or if you have a relatively low yield stress. Of course, it depends very much on the application and the materials being used. But once you start to get a significant yield stress, that's when the problems start to arise and the method becomes less accurate. Thank you.
Also, Paul, another question is regarding one of the slides you showed a pipe loop test. Is that a lot more effective way to measure the rheology than a rheometer?
The rheology using a rheometer is a standard way of doing things. I favor pipeline tests more. It's more of a, because of the, I suppose, the geometric similarity. We're doing pipeline tests because we want to do pipeline design. So it essentially gives basically similar, should give the same. And I've done many tests and shown that you can get the same. But what we don't get, if you use a rheometer, you won't get the tested critical velocity over a range normally of 3 or 4 different diameters, which is also an extra and very important bit of information, and not always that necessary, but that's one of the things which it can give us, which the rheometer would not be able to give. But essentially the two approaches can be used together and where necessary be used, and they essentially give the same results, but you can get a lot more information from the pipeline tests, looking at critical velocities and things like that. Thank you.
Okay, thank you, Paul. I've got also another question. It's regarding the Bingham model. It's widely used for designing pipelines. So is the Bingham model the most appropriate for mineral slurries, or should the Herschel-Berkeley model only be used?
That's an interesting question. It would depend essentially on the material characteristics. So once we've done a few rheological tests on the material, we'll be able to see whether we can use if the rheogram is flat enough to use the Bingham plastic model, or if it's going to be necessary to go to the extra curvature. If there's distinct curvature in the rheogram, then we will have to use the Herschel-Berkeley model. Thank you.
Okay, thank you, Paul. Also, there's another question about the next webinar, and will the next webinar cover the appropriate lab and pilot method to measure the rheology of slurries? In each webinar, we'll be looking at the specifics of each one, but yes, we will essentially be using the Herschel-Berkeley and Bingham plastic models, and we will certainly be looking at applications and the kind of data and information which would lead us to use a particular one in a specific case. Thank you. Okay, thank you, Paul. Now, I've got another question also regarding what is the typical pressure? Hello, Paul?
Charles, I lost you there. Yes. Please ask again.
Sorry. What is the typical pumping pressure
very much on the application, on the materials being used. If there is a very high static head to be overcome, we might have very high pressures. If we have a negative static head, we might not need to use pumps at all, and we could use gravity flow. So it's very much application specific, and we wouldn't be able to talk about a typical pumping head. Thank you.
Could you give us maybe just a range for a different type of material?
Well, it depends very much on the rheological characterization. So I think we sort of getting to the stage where if the yield stress gets up into over 100, we would really have a really high head. But it's difficult to say without looking at the specific application. Some of these will require positive displacement pumps where the really high heads are required. But most applications can be pumped using centrifugal pumps. So those heads are intermediate. It's really only the very high heads when one starts to use PD pumps. Thank you.
Okay. Now, Paul, I've got another question. What about the? Could you cover the calculation of wall shear stress in the pipe? And there is also another comment or another question, which is, does 8V over T, which is in your table, for the bulk shear rate, assume a Newtonian flow profile? And would it be different for a non-Newtonian?
That's a very interesting question, and it does. It definitely starts with what does a Newtonian fluid behave like in a pipe, and so that's where we get those formulations. But we stick to them. So those fundamental formulations don't change. What changes is the relationship between them. And so 8V over D, the bulk shear rate, that does come originally from how do we analyze a Newtonian pipe test. And the wall shear stress, which is D delta P over 4L, diameter, pressure drop over 4 times the length over the pressure tappings, that is a standard and is always used that way. Thank you.
Oh, also, Paul, would that be different for a non-Newtonian?
No. When we do pipeline tests, or we've got Newtonian fluids, or we've got slurries, the tests are always conducted the same way, the measurements are done the same way, and the data is presented the same way. What will change is the relationship and where the data lies. Okay.
I have another question. Is there a rule of thumb for a slurry to be able to flow into a centrifugal pump? And you say it was 60 megapascal yield stress. Do you have any comments on that?
The yield stress on its own is it's important to know it, but we need to know what the other flow characteristics are. Essentially, if you can get the slurry through the suction into the pump, it should be able to pump it. Once we get to very high yield stresses, the pump behavior can be affected. That would depend on each specific case. But the yield stress on its own, whilst it's important, it needs to be taken into account with the rest of the slurry characteristics as well. Thank you.
But do you have any rule of thumb? Is there any rule of thumb?
Once we're looking, I would say, in the range of around about 100 pascals, we would like to look at it more carefully. But it's very much making sure that the material can flow given the specific arrangement of the suction side of the pump. Thank you.
Okay, thank you very much, Paul. There was a last question. So thank you, Paul, and everyone for attending today's webinar. Now, if you have any other questions, please contact Paul or myself. You have the email address on this last slide. Once you leave today's webinar, also you will receive a survey on the presentation, and we would appreciate if you could complete it and provide your feedback to make sure the next one is better. You will also receive an email with a link to a recording of today's webinar. Now, thanks. I've got a really quick question. When is the next webinar? So I will. Paul is going to be away for a few weeks, but we'll try to organize the next webinar in about one month or a month and a half. So thank you once again thank you, Paul, and thank you everyone for joining us today, and goodbye.
Thank you, Charles. Thank you, everyone. Goodbye.